on Friday. If you can't remember where we were Friday, you came up to the chalkboard, remember, and put a bunch of Post-it notes up, and we were kind of talking about discontinuities and how limits can describe discontinuities. Well, I'm glad you're here today because I'm going to show you a test question. Good news right now is that there's no pressure, but it's still a good thing to think about today. And it starts to, again, tie together essentially everything in this chapter. You can write it down if you want. Ultimately, are you thinking about it? So true or false? If the limit as x approaches c of f of x exists, then f of x is continuous at x equals c. Now, for a little bit of audience participation, for a little audience participation. Do you ever do this where you had to sort of pick a side, maybe in, a social studies class? We're going to have you pick a side, but I'm not going to tell you which side. You're going to decide. If you think it's true, we're going to put you over here. If you think it's false, we're going to put you over here. So true is on the right, false is on the left. Just a little, by the way, it's not abnormal what you guys are experiencing. If you're like, oh my gosh, I'm doomed, because everybody's wrong. Don't think that way. Usually this is what happens, okay? Sometimes somebody realizes that it was false, but what do you guys think? Anybody, do you mind sharing? Why is it false? And or do you know what it means, what it takes to make it true? All right, well, here, sit down. Go ahead and sit down. It's still, you guys can still grab this and go, but I'm going to draw something if no one has anything. Do you think you know why it's false? You know what it would take to make it true. All right. Again, I'm going to help you a little bit here. Go ahead.
Because there's a hole in there.
So, because there's a hole in the graph, let me just add to that, there could be a hole in the graph. Based on this statement, there could be a hole in the, does the limit exist at C? Yeah, whatever that Y value is, maybe I should put something there, 2, 10, whatever. But is there a limit? Yes. Is it continuous? No, because again, there could be a hole in the graph based on that statement. Okay, so again, it's false because there could be a hole in the graph. Now be careful, I don't want you leaving thinking, okay, so there's always could be a hole in the graph. No, we have situations of other types of limits where there's not a hole, there's a jump, or there's an infinite. So there could be other types of situation, but this situation so far, a hole in the graph could fit. Now, how do you make it true? There has to be one more thing you would say. It's a little fancy. Okay, don't just say, well, fill in the hole. We're looking for something a little more mathematical. How do you make it so that it's true? Okay, you actually said it, okay, but you have to be thinking back to Friday. There was something that was said over here with some Post-it notes that had to do with continuous. Continuous. Well, it would be the value the value at C. You know what would have to be true about the value? In other words, f of C. It would have to equal 2. Now that's a fancy way of saying that that would be filled in, because the limit as x approaches C, the limit as x approaches C of f of x would have to equal the value, and they would have to be the same. The limit would equal the value. The limit would equal the value. Then it would be continuous. Okay, now this is a good statement to write down your notes, because this is what it means to be continuous. It means that the limit exists and the value is the same. Again, the limit exists and the value is the same. Then it's continuous. If you want to add my little sketch, if you want to put it kind of in sort of interpretive terms, the limit equals the value. Listen, you actually will see this as a test question. I mean, I would love if you kind of put it in your own words, but it is a very important idea in mathematics, because we like things to be continuous. When things are continuous, we don't have to worry about some kind of discontinuity. We don't have to worry about funny business. But what does it mean for something to be continuous? It's a calculus idea. It means the limit is the same as the value. Any other conversation with that? What can we do with this? What can we do with it? That's what we're going to spend this last part of this lesson talking about. One of the things we can do is honestly just answer some easy questions. I want them to be easy. I want you to understand that this doesn't have to be too hard. If you're able to look in a book, we'd like to basically answer some easy questions. Now, the reason I keep saying easy is because sometimes students try to make this too hard, like you're trying to make more of it than it has to be. So I just want to show you how we can take what we just talked about and answer a couple questions. You will see some of these in your assignment, but right now I'm just looking at a little graph that's in the left-hand margin. Are you looking at it also? It's just a little graph in the left-hand margin. Here's some questions that would match with this little graph. Again, let's not make these too hard. Does f of 2 exist? Now, f of 2 would have to be the value at f of 2. Or excuse me, at x equals 2. The value. Are you looking at that little point that's kind of like popping up off the, sort of like up above the graph, that little point? Okay, that's the value. So that would be a yes, and its value is y equals 2. How about the limit? How about the limit as x approaches 2? Now, are you looking at the little hole in the graph? Okay, that would be the limit as x approaches 2. So that intended height would be 1. That intended height would be 1. Okay, and then it lends itself to the question, is it continuous? Okay, now listen, you should definitely say it's not continuous because there's a hole in the graph. But it's also because the limit is different than the value. The limit is different than the value. Okay, so it's not continuous. But again, if you look at your answers for 1 and 2, they are definitely different. Again, it's supposed to be kind of easy, but that's what it means to be continuous. Here, try this one. Are you looking at the right place on the graph? F of 0. f of 0. Now you should be looking at that, if you will, that first point that's on the left side of the graph. That would be f of 0, and that of course equals 1. Now we can find the limit as x approaches 0. The limit as x approaches 0. This time you're just moving towards x equals 0, so you're moving towards that intended height, which is also 1. Okay, now I put this one in here because sometimes people aren't sure if something is continuous, if it's like a starting point. If the limit equals the value, then it's continuous. Okay, so is it continuous? Yes, even though it's like a starting point, it matches the definition, and so it's a yes. All right. Now, just to kind of summarize, I have one more of these little videos to show you. It should be a nice summary of what we've done yesterday and so far today. So just take a look here.
Chapters rely heavily on the existence of what's called continuous functions. In fact, most of your important theorems include a prerequisite that any function in question must be continuous before you could even think about applying the theorem. For example, the intermediate value theorem, which we'll also learn in this chapter, requires that the function be continuous. Well, in theory, continuous functions are predictable functions. They have no undefined points, no breaks, no holes, no jumps in the graph. But enough talk. Let's take a look at some pretty pictures. Now this function f is continuous, but these, g, h, and I, they're not continuous. Each of them, in fact, is discontinuous for a different reason at the x value of x equals c. See, now this one, on g, you've got a little hole in the graph. That's called point discontinuity. Over here on h, you've got a vertical asymptote that breaks the graph. Now this is called infinite discontinuity. And finally here on graph I, you've got a graph that just plain snaps in the middle. And that's called jump discontinuity. Now how can you judge just by looking at the graph of a function if it's continuous or not? Well, a continuous function makes a good bridge. Now see, if I drive across the graph of f, it holds up nicely. Whereas if I try to drive across the graphs of the other functions, I might either fall through or fall off. So, continuous functions are predictable. But what does that mean? Well, it means two big things. One, no breaks. Well, we already know that breaks occur in functions when no limit exists there. Therefore, for a function to be continuous, it must have a limit at every x in its domain. Secondly, no holes. Continuous functions must be defined everywhere in their domain. Mathematically now, we say that continuous functions have this property. For every x equals c in their domain, the limit as x approaches c of f of x is equal to f of c. In other words, not only does the limit exist at every point, but the height the function reaches for every x matches the limit.
Remember the little true-false activity? Okay, I just want you to hear it a different way. I mean, it's actually the same thing, but what makes something continuous? Okay, that statement in the middle, the limit is the same as the value. Okay, and of course, that would be the side that you would choose. That would be what you need to make every statement, to make every function continuous. You have to have a limit, you have to have a value, and they have to be the same. All right, now we have one other thing that we're going to do, but we'll start it now and it'll probably finish after lunch. And that is, we're going to do some fixing. We're going to do some fixing. And the book likes to call this, well, I like to call it fixing, because I think that kind of makes sense for kids. We're going to fix discontinuities. And you can write that down if you want. The book likes to use this language. And the language is fine. I just want to make sure you understand that it's the same objective. We're trying to fix a discontinuity. Okay, the book's going to call it creating an extended continuous function. Creating an extended continuous function. Now, the way that we will do this, and by the way, we actually previewed this a little bit Friday, so you might feel like in the next 10 minutes or so that you kind of saw this a little bit. The way that we'll do this is we're going to make f of c equal the limit as x approaches c. I'll show you how to do that, but you're going to feel like we've seen this a little bit. We're going to make f of c equal the limit as x approaches c. Okay, now I'm just kind of going slow because I've learned in the past that it just takes students a little time to process this. We're not in a hurry. I think once you get the idea, you'll realize, okay, how we're using limits, and we're basically using values, and then we're going to do this make thing. Okay, so I purposely kind of want to just take it easy here, make sure you get this idea. I did bring along, though, a special guest. Okay, do you know who I brought? Do you know who's good at fixing things? Bob the Builder. Bob, come on in. Hey, Bob, come on in. All right, so I brought along Bob. He's good at fixing things. I mean, geez, the guy can like fix a whole road in a day, build a barn, all kinds of problems. And so Bob, well, actually, it becomes a little more the question, first of all, can we fix it? I mean this in all seriousness. Is it going to be a yes, we can? And this is going to end up being the first thing that we try to figure out. So take a look at your function. We're not in a rush. We've got x squared minus 4x over x minus 2. Can we fix it? I know you just want to yell out, yes, we can, but we need to know a little bit first. Now, the first thing you need to know is the type of discontinuity. You have to know the type of discontinuity. And I realized I had this on the other screen. Let me show it to you. You might just want to read it. Remember, you can only fix a point discontinuity. Okay, now that's important, and you might feel like you heard that Friday, because you did. But just as a remember, you can only fix a point discontinuity, which gets us a little closer to kind of answering the question, can we fix it? Can we fix it? All right, you have to do a little math. Now, if you're like, should I graph it? Well, we could graph it, okay? But you'll see that I'm trying to appeal to some no graphing strategies, because that usually makes you stronger and better. So let's appeal to some no calculator strategies, like factoring. Now, what do you see here? What do you recall when you see? What happens when you have a common factor? What happens when you have a common factor? Every time there's going to be point discontinuity. So what's happening here, and to kind of spell it out, I'm going to spell out a couple things. Right now we're like classifying and locating. We just classified that there's point discontinuity. And in case you aren't sure why, it's honestly because we have a common factor. And every time. Okay. Now, while we're on the business of classifying and locating, we can give the location. And the location is simply going to be the place where you end up with a undefined x value. Again, some of this might sound a little familiar from Friday. We actually did it on one problem. But an undefined x value, don't make it too hard. It would be a 0 in the denominator. So it would have to be x equals 2. X equals 2. So, can we fix it? And can we fix it? Well, remember, the only thing you can fix is point discontinuity. So, can we fix it? Okay, now we can say, all right, now we can officially say that. By the way, the book likes to use the language that it's removable. Make sure you hear me out here. Removable implies that I'm removing the problem. That's why I like to use the language that I'm fixing it. So to remove the problem is to actually fix the point discontinuity, which, as you're going to learn, is to basically fill in the hole. So they use the word removable, and that gets kids confused because it's like, wait, am I taking out the hole? Well, yeah, you're taking out the hole by filling it in. So let's do that. Let me show you how we go ahead and fix this. So to fix it, what we're going to do is, well, first we're going to find the limit. So to go through this fixing, the first thing we need to do is we're going to find the limit. Now there's something I'm going to write here that I want you to be able to think about next time, but I'll show you this time, and that's understanding the place where I'm doing the limit. Okay, now let me say it again, the place that I'm going to do the limit. Now, it's not supposed to be a trick question, but it's the place where I have my discontinuity, x equals 2. Okay, so when I write the limit as x approaches 2, that took a little thinking about what's going on in this problem, because that's where the problem is. Now, the limit as x approaches 2 of f of x. Okay, we have to find it. Okay, we can continue. We can continue with the math that we were doing here. What I'm talking about is we can cancel the x minus 2's. Okay, now just so you realize, we just canceled out the problem, which is nice because now you can plug in x equals 2. You can actually do the limit. Now, you've done some problems like this. We did it back in the beginning of the chapter, but I plug in 2 and now actually get a value. Technically, what I got was the intended value, and of course, that's a limit of 4. Okay, so we found the limit. Now, I might have overdid a little bit, like I rewrote some numbers, but ultimately, I found the limit. Now, what we're going to do is we're going to fix it. Now, to fix it, we're going to make the value equal. Now, once again, I'm leaving some blanks here because I want you guys to be thinking. These are the parts I find kids get confused about. It's understand that there's like 2 numbers to fill in here. So I'm going to make a value equal something. Do you know, first of all, the place? Okay, now which number is that going to be? Okay, so we're going to make something equal 4. By the way, the limit is the thing that does the fixing. But once again, do you realize where we are? It's not supposed to be a trick question. It's the same answer. We're at 2. Why are we at 2? Way back in the beginning, we figured out that 2 was the problem. Now, how do we make f of 2 equal 4? Okay, well, by ultimately writing something. Okay, by writing something. Let's see if we can write this before the next bell. Because what I'm going to write is called an extended continuous function. Now, the extended continuous function is ultimately equal to my original function. Okay, my original function is okay. It's okay everywhere that x does not equal 2. Okay, so I don't want to like throw out that function. But here's the fix. And again, don't blink, sneeze, or leave because you're going to miss it. Here we go. We're going to fix. We're going to put the number 4. We're going to use the number 4 when x equals 2. And ultimately, that by writing that, I have filled in the point discontinuity. I have filled it in with the number 4. I appreciate you sticking around a moment there.